Welcome to the LF Energy Spring Summit. My name is Bruce Nordman. I do research at the Berkeley lab in California on energy use and efficiency in buildings with a focus on electronics and networks. Today I'd like to tell you about a technology called local power distribution. This is intended to sound like local area networking as we have with IT systems. The purpose of LPD is to make microgrids successful in the market. An operating system, like Linux, is essentially the dictator of a single device. It can see and control everything in the computer. Computers exist within Internet Protocol networks. Networks are a separate domain of technology, and networks do not have operating systems. They have services. A critical question for microgrid technology is whether its future lies mostly with a central control or with distributed control. Linux emerged after IP technology was already well developed, so Linux could just immediately implement it. For microgrids, there is no existing distributed or network technology for power for Linux to adopt. Microgrid technology today is usually proprietary and it requires expensive custom integration. This makes it not scalable, expensive, and not consistent with Linux principles. So, LF Energy for microgrids could improve proprietary technology, could create an open centralized technology, or create an open distributed control technology. We have technology systems for managing data flows and for managing energy flows. Each can be divided into a local and a wide area network. Network technologies manage the flows of a resource over space and through storage across time. Data packets are all different, so we use the Internet Protocol to route data across multiple hops from point A to point B. Conveniently, electrons are all the same, so routing them makes no sense. We only need to exchange power between directly connected devices. The modem separates local and wide area data networks. The utility meter separates local and wide area power distribution. Local technologies can and should be universal. Almost all local data exchange is done with Ethernet and Wi-Fi. The interface between the local and wide area networks should also be standard. How wide area networks are organized internally can vary over space and time, as can the physical technologies used on the wide area network. For data, we use the same mechanism, the Internet Protocol, for all scales and contexts. For electricity, we use in price and quantity in wholesale markets, at utility meters, and we can start to use pricing internally within buildings. Local prices are the foundation of local power distribution, its fundamental mechanism. As with IP, we can use the same mechanism at all scales. No device on the utility grid actually provides services to people. Substations, transformers, and power plants only generate or move power or stabilize system operation. Only within buildings do we provide services to people. And other than recently with PV and batteries, all buildings devices deliver services like light, comfort, or information. So we should expect the technology inside of buildings to be fundamentally different from the technology on the utility grid, and so need a different system architecture. In buildings, we have two domains of technology. The first is functional control for devices to know what their goals are for service delivery. The second is power distribution for moving electricity around in space and time. The diagram on the right shows network power integration, which is analogous to, but not the same as, the OSI model for data networking. The upper layers of network power integration are composed of the application layer protocols we have today. The lower layers are mechanisms for digitally managing the flow of electricity from one device to another device, analogous to how we digitally manage the flow of data from one device to another with Ethernet or Wi-Fi. For data, the Internet Protocol integrates the upper and lower domains. For power, each device integrates its functional control goals with its power distribution context to decide how best to operate. The two technology domains can evolve separately. Managing flows in a network context for data or power requires the addition of infrastructure devices. As we have seen with data networking, this model adds some complexity, but ultimately avoids much more complexity and greatly increases interoperability. A fundamental building block for networking electricity is digitally managed power. Standard DC power without communications exists today in cars with 12 volts and a standard connector. In both USB and Ethernet, communications are used to manage the quantity and characteristics of the power across the length, separately from the data communications that flow across the same cable. This allows USB and Ethernet devices to be plug and play for power. Similar concepts can be applied to AC power systems, but with less granularity than is possible for DC domains with power electronics. Combining digitally managed power with a local price allows us to move from what I call our unitary electricity system that we have today to a network model of power with multiple power domains that are loosely coupled. This model I call local power distribution. Just as data storage was essential to networking data, electricity storage enables networking electricity, so that storage is internal to each nanogrid controller. Any building's power distribution system might look like this diagram: residential, commercial, or industrial. Just as internet technology is independent of scale and the capacity of links or the complexity of a network electricity can also be independent of scale. A nanogrid controller might look like an Ethernet switch and could be an Ethernet switch. A nanogrid controller sets its local price and uses it to exchange power and manage storage. End-use loads use the price to optimize energy consumption over time. In this model, all communications about power occur only over a single link. There is no multi-hop communications about power. This has huge advantages for interoperability, privacy, and security. Even so, you may get a net flow of electricity across multiple links. For example, the PV panel on the left could have an effective price of 0 cents, and then send power to a grid controller, which might have a price of 10 cents, and then to another one at 12 cents, and then finally to one at 16 cents. Power can flow from the PV panel to the far right grid controller, even though they never directly communicate. Power links can be made or broken at will, and power flows will automatically readjust to take into account the changed system topology. This model enables a variety of features that are not possible with today's technology. We can have plug-and-play operation for generation and storage, not just end-use loads. Digitally managed power can detect anomalies and increase safety. Communication occurs before a circuit is energized to prevent overloading a wire. Networked electricity allows for arbitrary power topologies and power links directly between buildings. The local price allows fine-grained management of electricity, especially in situations where supply is limited. Communications have shown us that we can have technology that is universal across all building types and across all countries. We need to do the same for our next generation power technologies. Direct current power distribution, from local DC generation to local DC storage to local DC end-use devices, can save on capital costs and increase energy efficiency. Ultimately, this is the way to get to inexpensive microgrids for local reliability. Our utility grids in the US are becoming less reliable. Everyone deserves a microgrid for their most important devices. Today, every notebook PC is a microgrid. We need to build on successful technology approaches and then scale them up, rather than take expensive 19th century technology and try to scale it down. So, how do we get this to become a reality? I have a description of the system architecture for local power distribution, which can be formalized and adopted as an industry-wide standard. It contains only 4 messages, 3 of which are already in USB and Ethernet. We need to have these messages in existing and new power technologies for both AC and DC, and then have manufacturers sell products that implement that technology. The whole communications architecture is extremely simple for practicality, security, and interoperability. LPD is an excellent match for Linux. Thank you.